I just wanted to say that the particle work that we've done, or I've done, started sometime in 2014, 2015, and my first hackathon was in 2015, and in a meeting slightly before that, I realized that Renee was working on particles independent of me, and ever since then, I've had the pleasure of working with Renee on various particle algorithms, and we've published 2 papers at least, and that has included work with Wolfgang, which has also been quite a pleasure. So this is work with Mack, who is, I first met in his first year as an undergraduate, took a class from me, and he's been working with me pretty much continuously ever since, and full-time during the summer and whatever time we can get during the regular academic year. So to start, I don't know how many people are familiar with the way particles work. There is a particle, quite a large particle implementation now in Aspect, and I just wanted to show you computation that Renee and his colleagues made of a subduction zone in the way.
Gary, before you go ahead, you're not sharing your screen yet, in case you want to show us something at the moment.
My screen? I thought I said, oh, sorry. Okay, there we go. Whoop.
Yep, this looks good. Thank you.
Okay, great. So hang on a second, I gotta get the speaker view, or the, am I still sharing? Okay, good. And I'll put this in presentation mode. You wouldn't believe how many times I do this when I lecture. So, oops, that's not what I want. Excuse me for a second. So on the right is a picture of many particles. It was partly a paper for doing parallel computations and analyzing scaling the parallelism for the particles, but they're widely used in the computational geodynamics community. We're not the only one that uses particles. The particles, in this case, indicate where they started, red and blue, which I would call a passive tracer in some sense, because it's not being interpolated onto the underlying grid. Now, we're interested in particles that are active, and they can be density, viscosity, stress, an indicator function, which is not per se active, but it indicates where, in the case that I'm going to show you, a bending beam is. And common interpolation algorithms are averaging the particles in a cell. So you take, at every time step, you say this is density. You take the cell average of the values of density on each particle, and that is the value you place everywhere in the cell. And you use in the integration scheme so that then it goes into the computation of the velocity and the pressure. We have also worked with least squares. This L stands for linear least squares. Whoops, excuse me. And we're using the simple one without the XY term. And the least squares part takes the particles' positions and the particle values and computes the coefficients. Again, this is probably the first paper was Thielman, May, and Kaus that did this that I'm aware of. And then recently, Mack and I, or actually the first summer we were working together, we tried a quadratic one, and it has some interesting, one interesting property at least that I'll show you in a moment. So in a paper that we published, I don't know, 2 years ago or a year ago, with Renee and Wolfgang and a student I worked with, Harsha Lokavarapu, we showed that on a Q3 element on this SOL-KZ benchmark, which some of you may be familiar with, there are 2 benchmarks, SOL-KZ and SOL-CX. SOL-CX was done without particles in the first aspect paper, and it was shown it converged at the correct rate. And so what I'm doing is showing basically the accuracy by looking at the convergence rates. And what we discovered was that if you had a fixed number of particles per cell, say 4, that you would only get second order accuracy, even though with the Q3 element, this is an instantaneous problem where you put down, without particles, you put down the density and you put down the viscosity just like as an initial condition and solve. And then you look at, and then you let H go to 0 up to a certain point. And H is largest over here, smallest over here. And with the direct method, which is what we call not having particles, we get fourth order accuracy, which is what you expect without time stepping for the Q3 element. If we put the density on the particles and use the least squares algorithm, the linear least squares algorithm, we only get second order accuracy with a fixed number of particles per cell. If we increase the particles per cell as H goes to 0, in this case, we just fixed it at 4,096, which is not really practical. We can get up to third order accuracy. And with the Sol CX, we can get up to fourth order accuracy, but the number of particles per cell is just, it's not practical. So, sorry. So the first thing that Mack, and after a lot looking at, moving these squares and Merce boundary method and all sorts of various ways of interpolating particles onto the grid, we did what I would say is the simplest thing you could possibly do is just go from linear to quadratic. And lo and behold, we can achieve the fourth order accuracy in the velocity for a fixed number of particles. Now, since it's quadratic, we have to increase the number of particles per cell to 9. But on this simple, I always say it was a very simple test problem, but it's what everybody's been using, or at least Thielman, Kaus, and us. We can have fourth order accuracy for this problem with a fixed number of particles if we use the quadratic least squares algorithm. However, it's now part of Aspect. We put it in during the hackathon. We snuck in. We wanted to make the peak. We weren't at the hackathon technically, but we wanted to see the peak go up. So we did some pull requests during the hackathon. But I don't think we should use it yet. And why? Is because all of the particle algorithms, except for the averaging, all of the particle interpolation algorithms will overshoot and undershoot. And that's a problem. And it's not exactly the same kind of problem that you have when you vect, where you overshoot and undershoot. It's more of a what they call a Runge phenomenon in polynomial interpolation. Anyway, that's the problem we set out to fix this past summer. So I have a recommendation, and that is if you're going to use, if you want to shoot for second order accuracy, which is what the time stepping algorithm is in Aspect anyway, and you want second order accuracy in your spatial discretization, then use a linear least squares algorithm with a limiter. So you don't have overshoot and undershoot. And you can then get the fixed particle per cell, which was in the blue dots that were second order accurate. Now, if you have particles that are carrying components of, well, in the next figure, I'll show you particles that are carrying components of stress, and the 3 components of stress, and also what I call an identity particle or an ID particle that tells you when you're in the beam. This is a beam that's subject to gravity and it's a little denser. So it's going to go down and then we're going to turn gravity off and put it back up. I got it from John Nalaboff. It's in an appendix in a paper that I've forgotten at the moment. So the other thing I want to say is that this is the random particle distribution think there's 400,000 particles in this computation. It's in the benchmark folder in the master branch of Aspect. We discovered something interesting about this. Let me get this. I'm not perfect, but this is using not the regular averaging, but the nearest neighbor averaging. And I don't like it. Everybody that has worked with me knows I don't like random initialization. I don't see why people do it. I'd like somebody to explain to me why they think that random initialization is better. I think that the funny triangles that you're getting here are due to the pair view, the way pair view visualizes these things, but I'm not certain. So, oops, I should let this go a little longer. And you'll notice that it blows up. We call this the exploding vending beam. And as I said, this is in the benchmark folder. It uses particles. There's a compositional field version. It also explodes. Cedric has an idea about what's going on, and Renee has an idea, and they're not exactly the same. But something is going on with the standard algorithms, compositional fields, particles, and something right here just winds up being wrong. I don't know what it is. It's in the material model and how it's interacting with the particles. And I'll show you that. I mean, I'll try to convince you of that. So we developed a limiter that keeps the chi as the indicator function. And there's a certain number of particles. We're running with 9 particles per cell or 4 particles per cell. I'll tell you in a second. We have the band limiter as a PR that was open 12 days ago. And let's see. So here we have a fixed number of particles per cell. We're using what's called the reference cell. Everything's uniform in the cell. I'll show you in a minute how many. It's a very small number of particles, total particles. I'm only interested in limiting the indicator function between 0 and 1, which is what it should be. It's over here, and unfortunately, I haven't got the movie working now. This I call the neon lights, and if I had the background, the surface with edges, they only occupy 1 cell width, which is the best you can do, because as the beam moves down, sometimes half the beam is in a cell and the other half is the blue material in which it's on. And so you're going to get these colors that are between red and blue. But you'll notice with the limiter, we're staying between 0 and 1. And we've turned off gravity and we're going back up. We don't quite get back up to the top, but I do not think that has anything to do with the indicator particles. It has to do with the underlying material model. It could have something to do with the way the particles interpolate the stresses onto the grid. I'd like to work with John and others to try and understand this. So this is the, I asked Mack this morning just to double check. Here's the difference between what's in the particle version of the benchmark folder in the master branch of Aspect. It uses the random uniform particle generation algorithm, which can put no particles in a cell. And then you have to use your cell particle generator. It has around 400,000 particles, and it uses nearest neighbor interpolation. I would prefer the average myself, and I would as everybody knows, I prefer the reference cell. Our computations use the reference cell particle generator, and it only takes 60,000 particles. We use the linear interpolation, where we get the coefficients by least squares. And we have a limiter, which I call, it's based on a limiter that comes from gas dynamics and shock waves and finite difference community. We have some work to do on the limiter, but it isn't there is a pull request open. Thanks to Cedric, he gave us a problem to work on, and we discovered we have more work to do with our limiter. So in conclusion, we are working on limiters. I think that that's like one of the fronts that we need to be working on. The linear least squares interpolation algorithm is has been pulled in 2 and 3 dimensions. We've shown that the quadratic least squares, at least for the simple problem that we worked on, can achieve the highest order accuracy that the direct method does. In other words, no problems, no particles. And the caveat is that we've only looked at these simple KZ and SOL-CX problems. We do want to interact. We've been interacting with John Naliboff primarily, but I'd like to have more interaction with people using particles. I know Anne and Esther are aware of that. And I want to be motivated to meet your needs, or the aspect users' needs who use particles. Especially, I'm very interested in the rheology and the work that's being done in tectonic plates and earthquakes and so forth. Thank you.
Thank you, Gary.